Welcome to the Deep Dive. Today, we're taking a close look at something really fundamental for many people, lower limb prosthetic alignment.
That's right.
And for you, our listener, we've sifted through some, pretty dense material research papers, a detailed master's thesis from Sweden, actually, Jönköping University.
Yeah.
Our mission really is to unpack why getting this alignment right is so critical, understand what makes it, kind of tricky right now, and explore the new solutions people are working on.
Exactly. It's maybe not something you chat about every day, but how a prosthetic leg is aligned. It massively impacts comfort, stability, even the user's long-term health.
Right.
So yeah, we'll dig into why small errors can cause big problems and see how researchers are trying to make the whole process more accurate and consistent.
Okay, so let's jump right in. Why is this alignment piece just so fundamental? What actually happens if it's off?
Well, the sources are pretty clear on this. If that alignment isn't right, it throws everything out of whack. You've got decreased balance, obviously a higher risk of falls.
Yeah, you'd expect that.
But it's more than that. Poor alignment puts weird stresses on your other joints, knees, hips. That significantly bumps up the risk of getting arthritis there later on.
Mm-hmm.
And this might be surprising. It just takes way more energy to walk, like a lot more. Some studies suggest folks with transfemoral amputations might use, get this, like 80% more energy than someone with two biological legs.
80%? Wow.
Yeah. And bad alignment just makes that energy cost even higher. So it's not just feeling a bit awkward, It's got real tangible physical costs for the user.
That's a huge difference. So, okay, it's clearly not just about comfort. It links directly to health and just, daily energy levels. Now, something that came up a lot in the materials was this idea of subjectivity. Aligning a limb now is often quite subjective. What does that mean exactly?
Absolutely. So traditionally, getting the alignment right has relied, heavily on the prosthetist experience, their clinical judgment.
Yeah, eye for it, sort of.
Kind of, yeah. And while these professionals are incredibly skilled, that approach, it inherently lacks standardization. There's no universal validation, limited reliability checks, and it's hard to quantify.
Right.
Think about it. What one really experienced prosthetist sees as perfect might be slightly different from another's view.
Okay.
And the sources, they even point out that prosthetists themselves say they want better tools, a more objective way to really nail this critical step.
So they feel the limitation too.
They do. It's not just academics saying this. It means potentially, inconsistent experiences for the person actually using the prosthetic. Maybe not always the absolute best outcome possible.
Yeah, I can see that. If it's based so much on individual interpretation, variation is almost inevitable.
Yeah.
So could you walk us through the typical steps? How does this alignment process usually play out?
Sure. Generally, it happens in three main phases. First is bench alignment. That's done in the workshop before the user even puts the leg on.
Okay. Kind of a starting point.
Exactly. The prosthetist sets things up based on general guidelines, measurements,
Yeah.
a baseline. Then comes static alignment. The user stands still, wearing the prosthesis.
Ah, so now they're seeing it on the person.
Right. Observing posture, making maybe bigger adjustments. And finally, there's dynamic alignment. That's when the user starts walking.
The real test.
Pretty much.
Yeah.
This is where the fine-tuning happens, watching their gait, seeing how it moves, getting feedback. How does that feel?
Well,
it's iterative,
Yeah.
Observe, adjust, observe, adjust.
Okay. Set, observe, refine. Makes sense.
Yeah.
Now, the thesis mentioned anatomical planes, sagittal, frontal, transverse. For those of us without a medical background, how do these fit into making a prosthetic work well?
Yeah, they sound technical, but it's just a way to describe orientation in space.
Yeah.
Think of slicing bread.
Okay.
The sagittal plane cuts lengthwise left and right halves. That relates to forward and backward motion, like swinging your leg.
Got it.
The frontal or coronal plane cuts into front and back slices. That's about side-to-side stability, preventing leaning. And the transverse plane cuts horizontally top and bottom. That deals with rotation. Alignment means making tiny adjustments in all three of these planes to get smooth, efficient, natural-ish movement.
The bread slicing helps. Thanks. So 3 dimensions matching the body's natural movement. Let's talk hardware then. What are the actual bits and pieces of the prosthesis that get adjusted?
Okay, so a standard lower limb prosthesis has several main parts. You've got the socket, that's the custom bit that fits onto the residual limb. Super.
Right, the interface.
Exactly. Then the pylon, basically the main structural tube or rod. If it's above knee, you'll have a knee component, which is complex in itself. Then usually an adapter connecting the pylon to the foot. And finally, the prosthetic foot.
Okay.
Alignment is all about adjusting how these pieces connect their position and angle relative to each other to get that comfort, safety, and biomechanical function just right.
And the thesis brought up pyramid adapters and Cartesian coordinates. Sound like serious engineering.
It does, but the idea is pretty straightforward. Pyramid adapters are super common. Imagine two blocks, one with a pyramid shape sticking out, the other with a matching indent.
Okay.
They bolt together. By loosening the bolts, the prosthetist can tilt or slide one part relative to the other in typically two planes like forward, back, and side-to-side tilt. Little adjustments.
Ah, I see. Gives them that fine control.
Exactly. Other adapters might allow for rotation or shifting things slightly up, down, left, or right. And Cartesian coordinates the XYZ stuff. That's just a precise language.
Like map coordinates.
Basically, yeah.
Yeah.
Instead of move it left a bit, you can say adjust X by 2 millimeters, rotate around Z by 1 degree. It allows for really specific, repeatable adjustments. And that precision is key as we try to make alignment more, data-driven.
Okay.
Got it.
So we see why it's vital, the subjectivity issue, the process, the hardware. Now let's shift to fixing the problem. That Jönköping University thesis seems focused on finding better ways, better tools.
It really is. The researchers there saw the limits of just relying on visual checks and, the feel of it. So they aimed to develop new, more objective tools for clinicians.
Right.
And crucially, their first step was figuring out what the prosthetists actually need from a tool like that.
And they did that by just asking them, right? Talking to them.
Pretty much, yeah. They used in-depth, semi-structured interviews, talked to a range of clinicians to really understand the practical hurdles, the things they wish they had in their daily work, aligning whims.
Makes sense. Go to the source.
Exactly. And this wasn't just a quick chat. It led to identifying a really comprehensive list, 38 specific needs.
38, that's quite specific. Were they all equally important?
No, not quite. They grouped these 38 needs into categories like functional needs, physical aspects of the tool, who it should work for, what it should achieve overall.
Okay.
But importantly, they also had the clinicians rate how important each need was, so they could sort out the absolute must-haves from the nice-to-haves.
Smart. So what floated to the top? What were those key things the clinicians really wanted, the big pain points?
Several things really stood out. Any new tool absolutely had to be easy to use, intuitive, and safe, of course, for everyone involved.
Naturally.
It was also critical that it could handle unique patient anatomy and needs and work for both below knee, transtibial, and above knee transfemoral cases.
Versatility.
Yeah. And no surprise, precision and accuracy in measurements were right up there. High priority.
Makes sense.
But beyond just the function, they also wanted it to be a good investment for the clinic, something that would genuinely improve the overall quality of the prostheses. And this is interesting, be usable even for less experienced prosthetists. Help them get up to speed faster.
That list really covers a lot of ground: usability, patient factors, accuracy, economics, even training. It's complex. What about the tools they're using now? Did the study look at that?
They did, yeah. And it's pretty telling. The most common tool mentioned by the clinicians they interviewed, a simple vertical line laser.
A laser like from a hardware store?
Essentially, yes. It was originally designed for the construction trade, aligning walls, that sort of thing.
Huh.
So while it's found to use, maybe a basic one, in prosthetics, the study really highlighted this gap. Tools like that laser just don't meet all those high-priority needs the clinicians themselves identified.
So a clear mismatch between needs and current tools. Okay. So how did the researchers go from identifying needs to actually, designing potential solutions?
They used a really systematic design process. Started with things like brainstorming, just generating lots of raw ideas. Then sketching those ideas out, making them visual.
Okay.
They also did benchmarking, looking at existing tools, not just in prosthetics, but other fields too, for inspiration, seeing what tech is out there.
Yeah.
Then they used CAD computer-aided design to make detailed 3D models of the better ideal.
Getting more concrete.
Right, and even 3D printing early on to create physical mock-ups they could actually hold and evaluate.
Sounds very hands-on. They mentioned Pew matrices. What's that about?
Ah, yes. A Pew matrix is basically a structured way to compare different concepts. They listed their design concepts down one side, and the key criteria, like those clinician needs, estimated complexity, potential cost across the top.
Okay, like a comparison chart?
Exactly, but a systematic one. It helps you objectively score how well each concept meets each criterion relative to a baseline or other concepts. They started with about 70 rough sketches, refined those down to 13 conceptual sketches.
Wow, 70 down to 13.
Yeah, And then they used the Matrix process in a couple of stages, actually, to help narrow those 13 down further, focusing on the ones with the most promise.
And that careful selection led to actually building prototypes, things people could test.
Precisely. Based on that Pew analysis, they picked the strongest concepts. Then they built prototypes using CAD for the detailed digital plans and 3D printing to make actual physical versions.
Rapid prototyping.
Yeah, it lets you get something tangible quickly for user testing, for getting feedback. And eventually, 2 of their concepts made it to more formal prototype testing. They actually had people who used transfemoral prostheses try them out in simulated alignment scenarios.
That's great getting the end users involved, too, not just the clinicians. What was the reaction? How did the prototypes go down?
The feedback was really positive, actually, for both concepts. During the tests, clinicians used the prototypes, and afterwards they gave detailed feedback, rating how well the prototypes met those important needs: ease of use, safety, precision, value for money.
The checklist from before.
Exactly. And the ratings were consistently high. It strongly suggested that these new tool ideas really could improve the alignment process and genuinely meet those clinician needs better than what's currently available.
That's fantastic news. It really sounds like this work is hitting the nail on the head, addressing those core challenges. Now, the outline also briefly mentioned an article on user perspectives, but for upper limb prosthetics, how does that connect here?
Yeah, that article was about arms and hands, but it offered a really useful wider view, especially on user-centered design, which is totally relevant here too.
Okay.
It highlighted things like the trade-off users sometimes face between how a prosthetic looks, the aesthetics, and how well it works the function.
Right, form versus function.
Exactly. Some people prioritize one over the other.
Yeah.
It also talked about how important transparency is, like giving users clear info about repairs or maintenance. And it really hammered home the benefit of involving users throughout the design process.
So user input is key.
Absolutely. And those principles apply just as much to lower limbs. It kind of reinforces why the Jönköping study focusing on clinician needs, the people working directly with the users, was so important.
Totally. These devices are for people, after all. Their experience has to be central. Now, we should probably touch on the money side of things. Prosthetics aren't cheap, are they? What's the typical cost range?
No, they definitely represent a major expense. Sources suggest a transtibial below-knee prosthesis might be in the $6,000 to $8,000 range. A transfemoral above-knee one is usually more, think $10,000 to $15,000. And for the really advanced high-tech ones, could be $35,000 or even more.
Wow. And that's not a one-off cost, right?
Not at all. They usually need replacing every, say, 3 to 5 years because of wear and tear. And the socket, the part that fits the limb, might need replacing even sooner if the person's limb shape changes or there are comfort issues.
That's a huge ongoing financial commitment. Are things happening to make them more affordable or accessible?
Yes. Thankfully, there is work being done. 3D printing is a big area of hope here. It could potentially streamline manufacturing, cut down on custom mold costs.
Right, leverage new tech.
Exactly. And there are some amazing initiatives globally. The Jaipur foot from India is a famous example of a really effective low-cost design that's helped millions. And companies like Open Bionics are using open-source designs and 3D printing to push accessibility too. It's crucial work.
Definitely encouraging. Need to make sure these life-changing tools can actually reach the people who need them. Okay, so bringing it back to the alignment tools. What's the main takeaway for the future of getting prosthetics aligned properly?
I think the big takeaway, especially from that master's thesis, is that this kind of focused research and development is a massive step forward. By really listening to clinicians, understanding their needs, and designing tools to meet them, there's huge potential to make alignment more accurate, more objective, more efficient.
Moving beyond just the eye test.
Exactly. Giving prosthetists better data, better tools. It ultimately leads to better outcomes for the users, more comfort, better function, improved quality of life.
Okay, so let's quickly recap this deep dive. We stressed how vital good alignment is and the real downsides: balance, joint health, energy drain when it's off.
Right.
We unpacked the current subjectivity, the reliance on clinician judgment, and the expressed need for better, more objective tools. We walked through the typical bench, static, dynamic alignment stages and the key adjustable parts of the prosthesis.
Yeah, the socket, pylon, knee, foot, adapters.
And then we looked at that really promising work, like the Jönköping thesis, designing new tools based directly on clinician needs, with positive feedback from early testing.
Exactly. It's a great example of how understanding the needs of everyone involved, professionals and users, drives real innovation. These new tools point towards a more data-driven, effective approach. It could make a tangible difference.
It's been a really fascinating look at this. Amazing to see how research and tech are tackling such a core part of the prosthetic experience. Which leads me to a final thought for you, our listener. Considering these advancements in alignment tools and thinking about how sophisticated prosthetics themselves are getting microprocessor knees, adaptive ankles, plus this whole user-centered design focus, how might future alignment tools evolve even further?
That's a great question.
Could we see tools that get real-time feedback from the prosthesis itself? Maybe dynamically adjusting alignment based on how someone's actually moving or what terrain they're on. What might that future look like for an even more personalized, maybe even adaptive prosthetic experience?
Wow, yeah. Real-time adaptive alignment.
Definitely something powerful to think about. Thanks for joining us for this deep dive.